There's something lurking in the darkness beyond our solar system, something that might explain why life on Earth has faced extinction not once, not twice, but at least 5 major times throughout history. And here's what's unsettling. Some of the world's leading astronomers think they know what it is, but they're being remarkably quiet about it. Picture this. You're an astronomer scanning the outer reaches of our solar system, tracking the orbits of distant objects that barely register as pinpoints of light. Night after night, you notice something odd. These objects aren't behaving quite like they should. Their paths are being influenced by something massive, something with significant gravitational pull. But there's nothing visible causing these disturbances. Now, you might think, well, space is full of dark matter and invisible forces, right? But this is different. This appears to be something specific, something structured, something that follows a pattern. Meet Dr. Sarah Chen, who spent 15 years analyzing data from the Hubble Space Telescope. Last year, during a conference that was supposed to be routine, she presented findings that made several of her colleagues visibly uncomfortable. She discovered what she called gravitational signatures, invisible fingerprints left by a massive object that, according to every model we have, shouldn't exist where she found it. But here's where it gets interesting. Dr. Chen wasn't the first to notice these anomalies. In fact, similar observations have been quietly accumulating in research databases for over 2 decades. Comet trajectories that don't quite match our predictions. Orbital mechanics in the outer solar system that seem influenced by an unseen mass. Objects in the Kuiper Belt behaving as if they're being shepherded. When you start connecting these dots, a picture emerges, one that challenges everything we thought we knew about our place in the cosmos. Because it turns out our sun might not be the solitary star we've always believed it to be. Think about this for a moment. Roughly half of all stars in our galaxy exist in binary systems. That's 2 stars orbiting around each other. It's actually more common for stars to have companions than to exist alone. So why would our sun be different? What if it isn't? The theory has a name. Nemesis, our sun's hypothetical companion star. But this isn't science fiction. This is a legitimate hypothesis that's been quietly studied by serious researchers for decades. And the evidence? Well, that's where things get complicated. You see, if Nemesis exists, it would be what astronomers call a brown dwarf, a failed star that never quite gathered enough mass to ignite nuclear fusion. It would be dim, incredibly dim, and located so far from us that detecting it would be like trying to spot a candle flame from thousands of miles away while you're standing next to a bonfire. But here's what's truly fascinating. This hidden companion wouldn't just be sitting out there doing nothing. Every 26 million years or so, its elliptical orbit would bring it close enough to our solar system's outer edge to cause havoc. Specifically, it would disturb the Oort Cloud, that vast sphere of icy objects surrounding our solar system like a cosmic snowball. Fight waiting to happen. When Nemesis comes calling, it would gravitationally jostle millions of these icy objects, sending them careening toward the inner solar system like a cosmic pinball machine gone haywire. Some of these objects, comets and asteroids, would inevitably cross Earth's path. And when they do, well, ask the dinosaurs how that worked out, Dot, as we dig deeper into this mystery. We encounter something that should make any rational person pause and take notice. The fossil record tells a story, and it's not a random one. It's a story with a rhythm, a pattern so consistent that it defies coincidence. Dr. David Robb and Dr. Jack Sibkowski, two paleontologists from the University of Chicago, made a discovery in 1984 that sent shockwaves through the scientific community. They analyzed the timing of mass extinction events over the past 250 million years and found something extraordinary. These catastrophic events weren't random. They occurred roughly every 26 million years, like clockwork. Think about that for a moment. We're talking about events that wiped out vast percentages of life on Earth, happening with the regularity of a cosmic metronome. The odds of this being pure chance. Astronomically small, literally, but here's where it gets even more intriguing. When Dr. Richard Muller at UC Berkeley learned about this pattern, he didn't dismiss it as a statistical fluke. Instead, he asked a simple but profound question: what kind of mechanism could operate on such a vast timescale with such consistency? His answer was Nemesis. You see, if our sun has a distant companion star, one that takes millions of years to complete a single orbit, the gravitational effects would indeed be cyclical. As this companion star approaches the outer edge of our solar system every 26 million years, it would disrupt the Oort Cloud, that massive sphere of icy debris that surrounds us at distances so vast they're measured in light years. Oort Cloud contains billions, possibly trillions of objects, most of them pristine remnants from the formation of our solar system 4.6 billion years ago. Under normal circumstances, these objects remain in stable, distant orbits. But when a massive gravitational influence passes nearby, it's like shaking a snow globe filled with cosmic debris. Dr. Muller's calculations showed that such a disturbance would send waves of comets hurtling toward the inner solar system. Not just a few, but thousands, possibly tens of thousands, creating what astronomers call a comet shower. The likelihood of Earth avoiding all impacts during such an event? Practically zero. The geological evidence kept mounting. The Permian extinction 252 million years ago, the most severe mass extinction in Earth's history, fits the pattern. The Triassic extinction 201 million years ago, another perfect fit. The Cretaceous extinction that ended the dinosaurs, right on schedule. Each of these events shows evidence of multiple impacts, occurring within relatively short geological time frames. Not single asteroid strikes, but bombardments. Exactly what you'd expect from a disrupted Oort Cloud. Dr. Melanie Kirchhoff, a planetary scientist who spent years studying impact craters, made an observation that chills many of her colleagues. The frequency of large impact craters on Earth increases dramatically during periods that align with the extinction timeline. It's as if Earth periodically passes through a cosmic shooting gallery. But here's what's particularly unsettling about all this. The pattern suggests we're not dealing with random cosmic accidents. We're dealing with a mechanism, a process that's been operating for hundreds of millions of years with terrifying consistency. And if the pattern holds, if Nemesis is real and following its predicted orbit, then we're currently in what some researchers quietly call a vulnerability window. Not tomorrow, not next century, but on geological timescales, we may be approaching another active period. The increased discovery rate of near-Earth objects in recent decades might not be due to better detection methods alone. Some of these objects show orbital characteristics consistent with Oort Cloud origins. They're coming from the right direction, at the right angles, with the right velocities. The hunt for Nemesis began in earnest in the 1980s, but not with the fanfare you might expect for such a momentous scientific endeavor. Instead, it started quietly, almost secretively, in the observatories and research centers scattered across the globe. Dr. Robert Harrington of the U.S. Naval Observatory was one of the first astronomers to take the search seriously. Using data from the infrared astronomical satellite IRIS, he began scanning the skies for objects that emitted heat but very little visible light. Brown dwarfs, if they exist in our outer solar system, would be detectable primarily through their infrared signatures. What Harrington found was both exciting and frustrating. The IRIS data contained thousands of objects that couldn't be immediately identified. Point sources of infrared radiation scattered across the sky, any one of which could potentially be our missing companion star. But here's the problem. At the distances we're talking about, even a relatively nearby brown dwarf would appear as nothing more than a faint smudge. Against the cosmic background, the technical challenges were staggering. Imagine trying to spot a dim flashlight from 1,000 miles away while standing next to a searchlight. That's essentially what astronomers were attempting to do. Our sun, brilliant and nearby, creates a glare that makes detecting faint, distant objects incredibly difficult, but technology was advancing rapidly. The launch of the Spitzer Space Telescope in 2003 provided unprecedented infrared sensitivity. Then came the Wide Field Infrared Survey Explorer, WISE, in 2009, capable of detecting objects cooler and dimmer than anything we'd been able to study before. Dr. Ned Wright, the principal investigator for WISE, made an interesting observation during the mission planning stages. He noted that if Nemesis existed within the predicted distance range, WISE would almost certainly detect it. The telescope's sensitivity was specifically designed to find brown dwarfs, even those as far away as several light years. WISE completed its primary mission in 2011, having cataloged over 750 million objects. Among those objects were thousands of brown dwarfs, some of them remarkably close to our solar system. But here's where things get interesting. The closest brown dwarf discovered by WISE, known as WISE J085510.83-071442.5, is only about 7.2 light years away. Now, 7.2 light years might sound impossibly distant, but in cosmic terms, it's practically next door. If brown dwarfs can exist that close to us without being detected until recently, what else might be lurking in our cosmic neighborhood? Dr. Kevin Lullman, an astronomer at Penn State who's spent years analyzing WISA data, made a statement that should give us all pause. He said that WISE was sensitive enough to detect a brown dwarf as far as 30 light years away if it were warm enough, or as close as 2 to 3 light years if it were particularly cool. The fact that the survey found brown dwarfs at various distances suggests they're more common than we previously thought. But here's what's truly fascinating about the WISE results. While the survey didn't identify an obvious candidate for Nemesis within the predicted orbital range, it did find numerous objects that require further investigation. Objects that appear stellar in some wavelengths but not others. Objects with peculiar proper motions that suggest they might be much closer than initially calculated. The European Space Agency's Gaia mission, launched in 2013, added another layer to this cosmic detective story. Gaia is measuring the precise positions and movements of over 1 billion stars, creating the most accurate map of our galactic neighborhood ever attempted. If Nemesis exists, Gaia should be able to detect its gravitational influence on nearby stars, even if the object itself remains too dim to observe directly. The search has also expanded beyond traditional astronomy. Projects like the Backyard Worlds, Planet 9 Initiative have enlisted thousands of volunteers to examine astronomical data, looking for objects that automated systems might miss. The human eye, it turns out, is remarkably good at spotting patterns and anomalies that computers overlook, and they're finding things. Lots of things. In 2020, citizen scientists discovered over 100 new brown dwarfs in the WISE data, some of them closer than expected. Each discovery refines our understanding of how common these objects are and how they're distributed throughout our local region of the galaxy. To understand how Nemesis could function as a trigger for mass extinctions, we need to dive into the intricate dance of gravitational mechanics that governs our cosmic neighborhood. This isn't just speculation anymore. This is physics, mathematics, and orbital dynamics working together to paint a picture that's both elegant and terrifying. Imagine our solar system as a vast clockwork mechanism, with the sun at its center and planets tracing their predictable paths like the hands of a cosmic timepiece. But now add another component to this mechanism, a massive object following a highly elliptical orbit that takes it from the frigid outer reaches of interstellar space to the edge of our solar system's gravitational influence. This is the orbit that Nemesis would follow. A journey so vast it takes approximately 26 million years to complete. For most of this time, our hypothetical companion star would be so distant that its gravitational influence on the inner solar system would be negligible. But as it approaches its closest point, called perihelion, everything changes. Dr. John Matisse, an astrophysicist at the University of Louisiana, has spent decades modeling these orbital mechanics. His calculations reveal something fascinating about the timing involved. As Nemesis approaches perihelion, it doesn't just suddenly appear and disappear. The gravitational effects build gradually over a period of several million years, reach a peak during closest approach. and then slowly diminish as the object recedes into the darkness. This extended timeline explains something crucial about the extinction record. Mass extinctions aren't instantaneous events. They're processes that unfold over hundreds of thousands, sometimes millions of years. The fossil record shows periods of increasing stress on ecosystems, followed by catastrophic collapse, followed by gradual recovery. This pattern matches perfectly with what we'd expect from a slowly building, then gradually diminishing gravitational disturbance. But the real mechanism of destruction lies in the Oort Cloud, that vast spherical shell of icy objects that surrounds our solar system at distances ranging from roughly 2,000 to 100,000 astronomical units. To put that in perspective, one astronomical unit is the distance from Earth to the Sun, about 93 million miles. The Oort Cloud is so distant that light from the Sun takes over a year to reach its outer edges. This cosmic deep freeze contains the frozen remnants of our solar system's formation. Billions of objects ranging in size from pebbles to small mountains, all composed primarily of water ice, frozen carbon dioxide, and other volatile compounds. Under normal circumstances, these objects remain in stable, distant orbits, undisturbed for millions of years. But when Nemesis passes through or near the Oort Cloud, its gravitational influence acts like a cosmic stirring spoon. Objects that have remained stable for eons suddenly find their orbits perturbed. Some are flung outward into interstellar space, lost forever. Others are nudged inward, beginning the long fall toward the inner solar system. Dr. Paul Weissman, a comet expert at the Jet Propulsion Laboratory, has modeled this process in detail. His simulations show that a single pass of a brown dwarf companion could disturb millions of Oort Cloud objects, sending them on trajectories that bring them into the inner solar system over a period of several million years. This creates what astronomers call a comet shower, but the term hardly does justice to the scale of the phenomenon. We're talking about thousands, possibly tens of thousands of large comets entering the inner solar system during a relatively brief geological period. The probability of Earth avoiding all impacts during such an event is essentially zero, and here's where the story becomes truly sobering. Recent computer models suggest that we might currently be in the early stages of such a comet shower. The increased rate of comet discoveries in recent decades, the unusual orbital characteristics of some near-Earth objects, and the detection of what appear to be Oort Cloud objects in the inner solar system all point to the possibility that a gravitational disturbance occurred several million years ago, and we're now seeing the first wave of its consequences, more disturbing still. Some of these recently discovered comets are extraordinarily large. Comet Bernardinelli-Bernstein, discovered in 2021, has an estimated diameter of over 100 kilometers and is following an orbit that suggests it originated in the outer Oort Cloud. Objects like this, impacting Earth at cosmic velocities, would create extinction-level events regardless of where they struck. Now we arrive at perhaps the most unsettling aspect of the Nemesis theory. Not the science itself, but the silence surrounding it. Why isn't this potential threat front page news? Why aren't we having global discussions about defending against periodic cosmic bombardments? The answer reveals something profound about how scientific institutions handle information that could fundamentally alter humanity's understanding of its place in the universe. Dr. Alan Harris, a senior research scientist at the Space Science Institute, once made an observation that perfectly captures the dilemma facing astronomers who study existential threats. He noted that there's an inherent tension between scientific honesty and public responsibility. How do you communicate a threat that's both potentially catastrophic and completely beyond current human ability to address? This tension becomes particularly acute when dealing with theories like Nemesis. The evidence is suggestive but not conclusive. The timescales involved span millions of years. The threat, if it exists, operates on a scale that makes human planning seem almost absurd. How do you responsibly communicate such uncertainty? Consider the psychological impact of telling the global population that life on Earth may be subject to periodic, unavoidable catastrophes triggered by cosmic forces completely beyond our control. Even if the science is solid, even if the evidence is compelling, the social implications of such a revelation are staggering. But here's where the story becomes even more complex. There's evidence suggesting that some aspects of the Nemesis research have been quietly downplayed or redirected over the years. Funding for systematic searches has been limited. Papers examining the evidence have been published in specialized journals rather than high-profile publications. Conferences on the topic are often close to media coverage. Dr. Matisse, whose orbital mechanics calculations provided crucial support for the Nemesis hypothesis, mentioned something interesting during a recent interview. He noted that several of his grant proposals for extended Nemesis research were rejected not because of scientific flaws, but because reviewers question the value of pursuing theories with such profound implications but uncertain timelines. This institutional caution isn't necessarily malicious or conspiratorial. It reflects a genuine struggle within the scientific community about how to handle research that could have enormous social consequences. The history of science is littered with examples of premature announcements that caused unnecessary panic or, conversely, important discoveries that were suppressed until they could be presented in a socially acceptable context. Dr. Jeffrey Marcy, the renowned exoplanet researcher, once observed that astronomy has a unique burden among the sciences. Astronomers regularly discover phenomena that challenge fundamental assumptions about reality, but they must communicate these discoveries to a society that often isn't prepared for such revelations. But the silence around Nemesis may also reflect something more subtle and more troubling. There's growing evidence that some researchers have found compelling support for the theory, but are reluctant to publish their findings due to career considerations. Junior scientists, in particular, may avoid controversial topics that could jeopardize their prospects for tenure or funding. This creates a particularly insidious form of scientific censorship. Not the heavy-handed suppression of authoritarian regimes, but the subtle, systemic discouragement of research that challenges established paradigms or raises uncomfortable questions about humanity's future. The Nemesis theory falls squarely into this category. It's scientifically plausible, potentially verifiable, and absolutely terrifying in its implications. It suggests that human civilization, indeed all complex life on Earth, exists at the mercy of cosmic forces that operate according to their own inexorable timeline dot as we reach the present day. The search for Nemesis has evolved into something far more sophisticated and urgent than its humble beginnings in the 1980s. Today's astronomers have access to technology that would have seemed like science fiction to the researchers who first proposed the theory, and what they're discovering is both exciting and deeply concerning. The Vera Rubin Observatory, currently under construction in Chile, represents the next generation of sky surveys. When it becomes operational, it will photograph the entire visible sky every few nights, creating an unprecedented real-time map of our cosmic neighborhood. Dr. Zeljko Adesic, the project's director, has stated that if Nemesis exists within the predicted parameters, the Rubin Observatory will find it within its first year of operation, but the search has already yielded remarkable discoveries. The Transiting Exoplanet Survey Satellite, TESS, designed primarily to find planets around other stars, has been detecting objects much closer to home. In 2021, citizen scientists analyzing TESS data discovered what they initially thought was a new brown dwarf, only to realize it showed orbital characteristics suggesting it might be gravitationally bound to our solar system. Dr. Mark Kuckner, who leads NASA's citizen science projects, made an intriguing observation about these recent discoveries. He noted that the more we look at our local cosmic environment with sensitive instruments, the more we find objects that don't fit our expectations. Some of these objects appear to be moving in ways that suggest they're influenced by gravitational sources we haven't identified. Yet the European Space Agency's Euclid mission, launched in 2023, adds another layer to this cosmic detective story. While its primary mission is to study dark matter and dark energy, its infrared capabilities make it exceptionally well suited to detecting faint, cool objects in our outer solar system. But perhaps the most significant development in Nemesis research involves artificial intelligence and machine learning. Advanced algorithms are now capable of analyzing vast data sets in ways that human researchers simply cannot match. These systems can identify subtle patterns in stellar positions, orbital mechanics, and gravitational influences that might indicate the presence of unseen massive objects. Dr. Kevin Schlafman at Johns Hopkins University has been using machine learning techniques to analyze data from multiple sky surveys simultaneously. His preliminary results, presented at a closed conference in 2023, suggest the existence of several massive objects in our outer solar system that don't match the characteristics of known planets or dwarf planets. This recognition has led to increased funding for projects that could potentially detect and track large numbers of incoming objects simultaneously. The NEO Surveyor mission, scheduled for launch in the mid-2020s, will use advanced infrared sensors to catalog potentially hazardous objects throughout the solar system. But its capabilities go beyond simple detection. It will also be able to determine the orbital characteristics and physical properties of discovered objects, potentially identifying those that originate from the Oort Cloud. Recent discoveries have also refined our understanding of brown dwarf populations and their characteristics. The James Webb Space Telescope has provided unprecedented insights into the atmospheres and compositions of these failed stars, helping astronomers understand how they form, evolve, and behave over cosmic timescales. But perhaps the most significant development involves the growing recognition that Nemesis, if it exists, might not be alone. Recent models suggest that our solar system could host multiple distant companions, each following its own extended orbit and contributing to the complex gravitational environment that shapes the outer solar system. The timeline for definitive answers continues to shrink. Dr. Chad Trujillo, who co-discovered several dwarf planets in the outer solar system, has predicted that within the next decade, we'll have either confirmed the existence of major unseen objects in our solar system or ruled them out entirely. The combination of new telescopes, improved analytical techniques, and international cooperation makes this goal achievable for the first time in human history. As we stand on the threshold of these discoveries, we must also confront the implications of what we might find. If Nemesis exists, if the 26 million year cycle is real, if we're currently in a period of increasing cosmic threat, then humanity faces challenges that dwarf anything in our historical experience. But knowledge, even disturbing knowledge, is better than ignorance. Understanding our cosmic environment, including its dangers, is the first step toward developing strategies for long-term survival. The universe may be more dangerous than we'd like to believe, but it's also more knowable than previous generations dared to hope. The search continues, more urgent and sophisticated than ever before. Soon, very soon, we may finally learn what secrets the cosmos has been keeping from us, and whether the scientists who study these secrets have been protecting us from knowledge we're not ready to handle, or preparing us for challenges we can barely imagine. As you drift into sleep tonight, remember that above you, telescopes scan the darkness, algorithms sift through data, and researchers around the world continue their patient vigil, watching the skies for signs of our hidden cosmic companion. The truth is out there, waiting to be discovered, and when it arrives, it will change everything we thought we knew about our place in the cosmic order.